In this lecture, we're going to discuss the design of IIR, or Infinite Impulse Response Discrete Time Filters. IIR filters are less popular than FIR filters, but they come into play when we have particularly stringent specifications. And so it's important to know about them. So recall that an IIR discrete time filter uses both a moving average component, and that gives way to the numerator and the zeros of the transfer function h of z, and a recursive average component that gives rise to the denominator and the poles of the transfer function h of z. And the way that we design an IIR filter is basically by specifying the locations of the poles and zeros. Basically specifying these zero values, specifying these pole values, because once we know the zeros and poles, we know the transfer function, we know the A's and B's that define the implementation and therefore the impulse response, and we've really characterized the filter. And so the game here is going to be about poles, both placement of poles and zeros. It turns out that IIR filter design doesn't have quite the same elegant mathematics as FIR filter design. Moreover, there isn't a really straightforward way to derive IIR discrete time filters from first principles. To the contrary, what we typically do to design an IIR discrete time filter is a two-step process that's just a little bit ad hoc. In the first step of the process, we design an analog filter. Okay, we haven't talked about this at all in this class. Analog filters are built out of resistors, capacitors, and inductors, and they process continuous time signals. So this is really out of scope of the class, but this is what is used to design discrete time filters. Is first we design an analog filter. In this case, instead of using the Z transform, we use the continuous time counterpart, which is called the Laplace transform. The theory of designing analog filters is very well established, but it's also, as I said, well beyond the scope of this course. So now, in step two, armed with this analog filter design, we transform our analog filter using a conformal map. And the most typical one that we use is something called the bilinear transform. That basically, we just take the Laplace transform analog filter design, given here, and we replace the Laplace variable s in the following way. We just sub in, instead, for every s, we sub c over z minus 1 over z plus 1. And it turns out that if the Laplace transform transfer function of the analog filter is a rational function of s, which is what happens when we design analog filters, we will get a rational transfer function for our discrete time filter h of z. So it's a little bit of an opaque procedure, and therefore we're not going to talk about actually doing this process in this course. We're just going to look at the three main families of analog filters that fall out into the three main families of discrete time filters. And those are, as we're going to see over the next few slides, the Butterworth filters that have very nice properties. In particular, the fact that they have no ripples or no oscillations in their frequency response. The second is actually a family of two filters, Chebyshev 1 and Chebyshev 2 filters. These have ripples, but they have ripples either in the passband or the stop band, and not both. And then the third class are the so-called elliptic filters that have ripples in both the pass and the stop band. These are very powerful but very dangerous filters, and just use these with caution. Okay, so let's spend just a few minutes looking at these filters, talking about them, their properties, and then some examples of each so you can compare and contrast. So let's start with the Butterworth filter. The Butterworth filter has a very nice property that it first of all, it has no ripples. So you see it's very, very smooth. and it's very, very flat. You can look how flat the response is here around the frequencies 0 and pi. And in fact, the Butterworth filter is the most flat possible filter at the frequencies 0 and pi. And the way that we make it the most flat possible is we look at a Taylor expansion of the frequency response around the frequencies 0 and the frequencies pi. And basically we try to set the most number of derivatives of this Taylor series to 0, which is what gives us this very, very flat response. That's very, very useful for applications where you don't want ripples. A Butterworth filter has n zeros. It has n poles. All of the zeros are located at the point z equals -1. And all of the poles are located on a circle of some radius, potentially, very large, inside, but always inside the unit circle. And there are actually formulas for these zeros and poles, but the formulas tend to be rather complicated. The nice thing is there's a command in MATLAB, the butter command, that will design you a Butterworth filter automatically. And here's just an example of a 6th order, n equals 6 Butterworth filter that has 6 delays in the moving average component, 6 delays in the recursive component. Here's the frequency response. You see the transition is fairly rapid. And here is the impulse response, which it's causal, so it's 0, and then it basically rings on for basically an infinite amount of time, but decaying fairly rapidly towards 0. So this is the Butterworth filter. When you can tolerate this fairly slow transition from the pass band to the stop band, this is the filter of choice. Next, the first of our 2 Chebyshev filters, the Chebyshev type 1 filter. This is a filter that has oscillations in the pass band and no oscillations in the stop band. It also has n zeros and n poles. Again, all of the zeros are at the point z equals -1. And now the poles are located not on a circle, but an ellipse inside the unit circle. And here's an example of a n equals 6, a 6th order Chebyshev 1 filter designed in MATLAB. And you see the very interesting idea that we have equal ripple, right? The ripple has equal amplitude inside the passband, and then a more rapid decay towards the stop band or transition, and then no ripples at all. Very Butterworth-like behavior in the stop band that's due to all of the zeros at z equals -1. And here is this impulse response of our Chebyshev 1 filter. Useful. The Chebyshev 2 filter, potentially a little bit more useful than the Chebyshev 1. It's just like the Chebyshev 1, but now the ripples have been moved from the pass band to the stop band. So now you see we have equal ripples in the stop band. It turns out this is usually more useful for a lot of the specifications that we have for designing digital filters. And these filters are just a little bit more complicated pole zero-wise than the Butterworth or Chebyshev 1. We still have n zeros and n poles, but now the zeros, they're all on the unit circle, but you see they're distributed. They're no longer all at the point -1. They're actually distributed around the unit circle, and if you think about it, they're at precisely the frequencies, okay, that correspond to these angles. These angles in the z-plane. So this angle corresponds to, let's just draw these here. This first angle corresponds to this first 0. The second angle corresponds to our second 0, etc. And this is an example then of a Chebyshev 6 filter designed, or rather, Chebyshev 2 filter designed using a filter order n equals 6. The zeros are on the unit circle, and again, you see that the poles are on an ellipse and inside the unit circle. And here's our impulse response. And it's interesting, if you just flip back and forth through these slides, it's very difficult to tell these filters apart by the impulse response. It's very easy by looking at the frequency response. So the last filter is the sort of the big hammer IIR discrete time filter. It's the so-called elliptic filter, and it has oscillations in both the passband and in the stop band. Right, it has oscillations in both. Very important. The oscillations do not have to be the same size. They can be much smaller in the passband and larger in the stop band, and vice versa. These filters have a very different kind of structure than the previous filters. Again, still N zeros and N poles, and still the zeros are all on the unit circle, corresponding to these frequencies. Right, you see these frequencies that correspond to these angles. But now you see the zeros and the poles are very tightly clustered around this transition band from the pass band to the stop band. And it's this clustering with pole. Notice this pole here extremely close to the unit circle, and there's another one even closer to the unit circle. It's these poles very close to the unit circle that gives it both this very steep transition and also a very pretty wild behavior potentially in practice. And so if you just think, for example, of implementing a filter, an elliptic filter using finite precision arithmetic, it's very easy to design an elliptic filter, for example, where a pole will slip outside the unit circle and become Bibo unstable. So elliptic filters, you should really think of them as a big hammer, and they should only be used when you have an extremely stringent specification that you have to meet. So here's a quick comparison of all of these filters overlaid with each other, and you can see very nicely whether these filters have oscillations in the pass band, oscillations in the stop band, and also you can see that the Butterworth has by far the most gentle transition from pass band to stop band, right? Followed by the red and blue Chebyshev 1 and 2, and these actually have a similar transition width. They just look different here because of the way I've offset the curves so you can see them stand apart. And then finally, you see the extremely steep green elliptic filter transition that is really a hallmark of that particular filter. So basically, given a certain specification that you need to meet and a certain order that you're allowed, N, which specifies your number of delays, multiplications, and adds, I would recommend that you start with Butterworth filters. If they don't work with your spec, you move to Chebyshev 2. If that doesn't work, then you need to bring in the big guns, the elliptic filters. So in summary, what we saw is that IIR filters use both a moving and recursive average. They have both poles and zeros, and it's really the poles that allow them to have a really steep transition from the pass band to the stop band. There's no really elegant, direct derivation method for designing discrete time IIR filters, and so typically we use this somewhat ad hoc, but still beautiful transformation procedure where we design an analog filter and then use a bilinear transform to bring it into the discrete time domain. We looked at the fact that there are 4 families, really 4, of IIR filters: the Butterworth, Chebyshev 1 and 2, and elliptic filters. We saw that there are commands, Butter, Chebby 1, Chebby 2, and ellip, that are available in MATLAB for designing filters, which are very handy. Moreover, there's some very useful commands in MATLAB I recommend you check out that will basically help you choose the filter order given that you have a specification that you want to meet. And these are the Butter ORD, Chebby 1, Chebby 2 ORD, and ellip ORD. So I highly recommend that you play around with the Butter, Chebby, and ellip commands. You run those into Z-plane to plot the poles and zeros. build filters and use filter to filter signals and see what these filters do to signals. And then finally, look at these order selection commands to help you select the order that's just right for your particular spec.